Yeah, hi. I'm Thorben Kastenholz from the University of Bonn, and today I'm going to speak about the computability of the minimal genus and second homology. So let me just get my presentation. Here we go. So all I'm going to talk about today, or today doesn't even make sense, but right now, is joint work with Mark Pedon, and it is based on a recent paper by me and Mark Pedon. So let's get right into it. So what exactly is the minimal genus, and what is a quite related invariant named chi minus? So notice that every second homology class can be represented by maps from surfaces to our space X, so that the fundamental class of S of the surface gets mapped to the corresponding homology class. Here, when I say surface, I mean a compact, oriented surface, closed, but it doesn't have to be connected. So this is quite important. And so what one can do is one can use complexity invariance of the surfaces to produce geometric invariance on second homology. The two main examples are given by the genus, where the genus is meant as the sum over the genera of the connected components, and chi minus, which is basically minus the Euler characteristic modulus spheres. So if you look at this maximum here, it basically gets rid of sphere components. And this will be a theme throughout this whole topic, that somehow sphere components or spheres behave a little bit differently than other surfaces. And so sometimes you want to get rid of them or somehow ignore them a bit. So using these two complexity invariants, one can define the minimal genus and the minimal chi minus of homology classes by taking their respective minima over surfaces representing these classes. And of course, this is related to two things I want to mention right now. First of all, there's the commutator length, where you basically have a curve inside of a space. I mean, of course, from group, this is more like a space perspective on the commutator length. But if I have a curve in a group, in a space, and I'm considering surfaces that bound this curve. And then I'm interested in the minimal genus of these surfaces. This is essentially the commutator length of that curve, of the corresponding element in the fundamental group of my space. And so in light of that, this is somehow like an absolute version of the commutator length. Another thing that is quite related is people have studied this question under some restrictions on X and the maps you're considering. So if X is a manifold, one might ask the map to be an embedding. And there has been a lot of research into this case when the dimension of X is 3 or 4. In dimension 4, there's a lot of stuff related to the Thom conjecture and the symplectic Thom conjecture. And stuff like that. And I'm not really going to talk about that anymore. In the case of free manifolds, there's actually a lot known about chi minus and embedded chi minus. Namely, this embedded chi minus already has a name, namely it is the Thurston norm. So this is the minimal chi minus among all embedded surfaces, while our chi minus just use arbitrary maps. There's also a related invariant called the Gromov norm, which is the minimal L1 norm of real singular representatives of my homology class. And then there's this quite long chain of, well, it's not all equalities or inequalities, and there's also a limit in there, which starts with the Thurston norm on the left-hand side, which certainly is bigger or equal than chi minus, just because chi minus just is a minimum over a bigger set. And it's quite easy to see that we also have this inequality here, because a representative of n times alpha can always be given by taking a representative of alpha and precomposing it with an n-fold cover, which of course multiplies the Euler characteristic by n. And then there's a theorem by Gromov, which tells us that this converges to halve the Gromov norm. And now there's a theorem by Gabay, which tells us that the Gromov norm, or half the Gromov norm, is actually equal to the Thurston norm. So if you So we have this chain of equalities here, where on the left-hand side and on the right-hand side is the same. So all of these things agree. In particular, chi minus and the first norm agree. So in the case of free manifolds, it doesn't really matter whether we take embedded representatives or just arbitrary representatives. This produces the interesting property that for free manifolds, chi minus is actually multiplicative. So if we're considering n times alpha, then we can pull out the absolute value of n. This is far from true in a general case, and we will actually see an example of that, I think. What you can also get from this chain of inequalities, even though it is true, much more general, is that the genus and chi minus agree up to a factor after stabilization. This is true for all spaces, and I'm going to come to that in a couple of slides. But the important thing to note is that there are free manifolds where no minimal genus representative can be embedded. So in particular, you can immediately, just in this very easy case of free manifolds, you can already see that there's quite a distinction between minimal genus and minimal chi minus, even though the invariants are quite related. In order to capture this difference between the minimal genus and minimal chi minus, we define what we call the attainable set. So the attainable set is a subset of R2, or rather of Z times 2Z, associated to a second homology class, where we take all possible pairs of values chi minus comma genus for every representative. And the important thing to note is that this only depends on the group, the fundamental group of our space X. In the following sense, namely, for every space, we have a map from X into a K pi 1 of X1. And the attainable set of a class alpha and the attainable set of the image of that class under the map I just mentioned agrees. In particular, there's an old theorem by Hopf, which tells us that the kernel of the map from the second homology of X to the second homology of the fundamental group is just the image of the Hurewicz map. And of course, the image of the Hurewicz map is just the classes that are representable by spheres. So in a sense, this tells us that if we get rid of spheres, we just end up with group homology. So this allows us to say that to restrict ourselves to two complexes, since all two complexes yield all fundamental groups or have all fundamental groups. So, for example, if you're interested in the minimal genus problem for whatever kind of space, you can just take its two skeleton and compute the minimal genus problem there to solve the minimal genus problem for the bigger space. So in that sense, we restricted ourselves to two complexes here because two complexes are far more easily tractable than higher dimensional complexes. And our methods actually explain how to compute the attainable set for many kinds of two complexes. First of all, one of our main theorems, and we can only paraphrase it, it's kind of hard to really state it because it's a bit technical, is that we can actually compute the attainable set for certain two complexes, which include quotation marks negatively curved two complexes, where here negatively curved two complexes means two-dimensional cut minus one complexes. We can actually compute it for a bigger class of spaces, but it's kind of hard to really pinpoint or give a definition or a concise definition of for what kind of spaces we can actually compute this. It needs some kind of weight function, and we don't really have a structural result of when such a weight function exists. On the other side, one might ask, okay, negatively curved two complexes is kind of a bit strict. What about the general case? And then we have proven that the general case is actually undecidable. So there can be an algorithm that decides whether the genus or chi minus is actually even bounded by a certain B. And in the second half of the talk, I will somehow explain how to, I will give an idea of the first part, how this actually works, and I will give, I think, almost a complete proof of the second half. But before that, let me talk a bit about the attainable set first, because the attainable set is quite interesting, and I think it deserves a little bit of focus right now. So let's start with an example where we have the following gluing pattern of these three octagons, where we identify the once dashed lines with each other, and we identify the twice dashed lines with each other. And we also identify opposite sides. So we identify this side with that side, this side with that side, this side with that side, and so on. So the space we get is basically built from three surfaces of genus 2 glued together along simple closed curves. And one can easily see just from this description that the second homology has actually rank 3. And the class we're going to be interested in is the sum of the three cells. So it's basically this surface of genus 2, this surface of genus 2, this surface of genus 2. And this is what the attainable set looks like, or it's basically just a part of it. It continues indefinitely upwards, and it's all, and basically all the points above this line here, which lie in 2z times z, are always in the attainable set. So what exactly are these interesting corners here of the attainable set? Well, this here is a surface of genus 6, which has Euler characteristic 6. So this is actually given by just a surface of genus 2, surface of genus 2, surface of genus 2. So these are just basically the three cells themselves. Then there's this class here, which is basically given by taking, for example, just a contour of these two octagons, which gives you a surface of genus 4, and this cell here, which gives you a surface of genus 2. So these are given by a surface of genus 4 and a surface of genus 2. And then there's this guy here, which is going to be just a contour of this gluing pattern, which gives you a surface of genus 5. And already you can see kind of a slogan, namely the chi minus minimizer somehow wants to be as disconnected as possible, because having many connected components somehow decreases the Euler characteristic, while the genus minimizer somehow wants to be as connected as possible, right? This here is 3 surfaces of genus 2, while this here is 1 surface of genus 5, sorry. So let me come to some basic properties of the attainable set. And maybe let me get into some detail about these 3 things, because I think they're kind of hard to understand just from the formulas. So the first thing says that the attainable set lies in between this line here, which is the minimal chi minus line, and this, and above the minimal genus line. This is kind of obvious from the definition. And then it's also always above this line here, starting at n0 and then going with this, going up like that. Where this, what is n0 actually? N0 is the minimal number of components, of non-spherical components I need to represent my class alpha. So for example, if I have like for example, in our previous example, n0 was just 1. Because I just need one connected component. But for example, if I have the disjoint union of 2 surfaces of high enough of genus bigger or equal than 1, then n0 would be 2. While, for example, for the fundamental class of the 2 sphere, it would just be 0, because then we can just represent it by a sphere, so there's no need for a non-sphere connected component. So what does this condition here actually means? It just means that the attainable set is contained in this cone here, cut off by this genus minimal line. And so what does the second thing mean? Well, the second thing means that whenever I have a point in the attainable set, then I can go upwards to once upwards, or I can go to the top right. And what do these steps geometrically mean? Well, going upwards once just means I take the disjoint union with a torus on which my map is null homotopic, which of course increases the genus but leaves the Euler characteristic the same. While going to the top right just means I take the connected sum with a torus on which the map is null homotopic. And then there's this last step, which is somehow like a conditional move, that as long as we're above this line, I can always go to the right. And what does this here mean? This just means I take 2 non-spherical connected components and connect them by a path. And then, or basically take the connected sum of these 2. And of course, I can only do this as long as I'm not on the minimal number of non-spherical components. And this immediately gives you that, for example, the genus representative here can always be chosen to be as connected as possible, while somehow the chi minus minimizer is somehow very far away from this line here. So it's somehow as disconnected as possible. So this is what I meant before by having these different kind of objectives to themselves, that somehow they want to be as disconnected or as connected as possible. There's much to be said about the structure of the attainable set. So it always looks like this, that we always have these steps here. This just basically just comes from these kind of steps, these steps we have here. And it would be interesting to know what kind of structure actually can arise as attainable sets. There's something else you can do, and this should be seen in parallel to how you can stabilize the commutator length. One can also stabilize chi minus, or the genus, by taking these limits here. And of course, one can also stabilize the attainable set. And here's a proposition of us that basically once I do that, all the fine structure of the attainable set vanishes. Namely, the genus and chi minus basically become the same invariant, and the attainable set is completely determined by the stable chi minus. So what you see here is actually the scaled multiplicatives of the attainable set we had in the previous example for multiples. And then you can basically see that the attainable sets just move closer and closer to this triangle here. And in the end, it's just going to be this triangle here. So this is somehow similar to how the stable commutator length becomes blind to many subtleties of how different you could define the commutator length. So similarly here, somehow all the fine structure just vanishes. So let me just finish this the first part of my talk with the following two questions. So first of all, this is something that Mark and I are actually thinking about right now. Namely, can one use other complexity invariants of manifolds to produce geometric invariants of Bordism or singular homology? So higher degree homology classes can also be represented by manifolds. And so, for example, third homology can also be completely represented by three-dimensional manifolds. So one could use, for example, say the Higa genus or the simplicial volume of three manifolds to produce invariants of three manifolds. And it would be kind of interesting to see what they actually measure and how well one might be able to compute them. Similarly, one could use just could do this for higher degree classes. But then it somehow becomes a little bit more, say, natural to use Bordism homology, as not every singular homology class can be represented by manifolds, nor is the map from Bordism to singular homology injective, meaning that there are some weird relations about manifolds representing the same singular homology classes. So one could use Bordism homology for that and then just use invariants of the Bordism classes. And one thing we're thinking about is what kind of sequences of Betti numbers can occur, which is of course just one example. There are many more examples one could think of. So I think this might be a very rich topic because I think it might give more insight on how actually singular or Bordism homology works and what it actually measures. The second question I have is about the mapping class group of surfaces. So it's a theorem by Hara that the second homology of the mapping class group is just given by Z plus some torsion part. So a question I would be interested in is what is actually the minimal genus of these classes and whether it does depend on the torsion part. And the dual question to that, which basically deals with the second cohomology here, has earned a lot of focus in the last couple of years. Namely, it is the question, what is the minimal genus such that there exists a surface bundle with genus G over the surface of genus H, such that the total space has non-zero or say fixed signature. And of course, this is somehow like the dual problem because basically the second group homology here is generated by measuring this signature of this of the total space. So yeah, with that, I'm gonna finish my first part here.